Hey, welcome back everybody. In this section we're going to work with binary numbers in a little bit different way, and we're going to see how real numbers can be stored. There's a lot of different storage systems in use, and this is an old system. We're going to look at the IEEE 754 number storage scheme, but it's a simple way to see one way we can store positive numbers, negative numbers, decimals, integers, and really large and small numbers, all using the same system. So let's jump right in. Okay, so the IEEE standard requires us to be able to do two things. First of all, recognize and write real numbers in normalized binary form. We'll do that first. And then use 32 bits to store that normalized binary form along with the exponent and the significant digits in the number. So let's start by looking at what's called normalized binary form. So first of all, what does it mean to use normalized binary form? To write a number in normalized binary form, we first write the number in binary form. So let's do an example here. Let's take the number 25 in base 10. Let's express that in binary form. I'm just going to do one of these. Later on in this lesson, I'll skip this step, but as a little refresher, we make a binary conversion table. The biggest power of 2 that fits into 25 is 16, so that's where our first 1 will be. 25 minus 16, that leaves us with 9. 8 fits into 9 once, and that leaves us with 1 left over. So the representation of 25 base 10 is 11001. The second step, now that we have it in binary form, is we write that in what I like to call binary scientific notation. That is to say, when we were working with numbers in scientific notation, for example, if you had the number 9300, we could write that in scientific notation by moving the decimal all the way to the left, so that we would have one number to the left of the decimal, 9.3, and then we put all those decimal places up as a power of 10. So we moved it 3 places, and this is a large number, so that would be 10 to the third. Well, we can do the same thing for this binary number. We can take the number 11001 and we can express that in a sort of binary scientific notation. We're going to move our decimal, in this case, 4 places to the left, and this becomes 1.1001. In normal scientific notation, we're working with base 10, and every decimal point represents a power of 10, so we use 10. Here, in binary, these are all powers of 2, so that's why I like to call it binary scientific notation, so it's times 2, and since this was a bigger number than 1, we moved it 4 binary places. We get 1.1001 times 2 to the 4th. And that's it. This is normalized binary form. Let's do another example of that. Let's convert negative 72.31, there's a decimal on here, base 10, into binary and normalized binary form. Well, remember that the first thing we do is we convert to the negative 72. So for the purposes of what we're doing here, we're just going to leave the negative sign out in front. We're going to turn that into a sign bit in just a minute. But negative 72 then will be negative 1001000, and you could make a binary conversion table to do that. I'm not going to take the time to do that. I'll bet you can do that at this point. Verify that. That's a 64, no 32s, no 16s, and an 8. 64 and 8 makes 72. But this number has decimals after it. I'm using red not because this is wrong, just want to make it stand out here. So we have to have some binary places on our number as well. And if you remember, the process to do that is really easy. We take our number 0.31 and we start multiplying it by 2. If we multiply that by 2, we get a 0 in our first binary place, times 2 again. There we get a 1. Subtract off that 1, multiply it by 2 again, and we get a 0. Times 2 again, we get another 0. Times 2 again, there's a 1. Subtract off that 1, times 2 again, there's another 1. Subtract off that 1, times 2 again, there's another 1, and we can go on as long as we want here. That's far enough for our purposes. So at this point, we can see that negative 72.31 base 10 is the binary number shown here. You've done that before. If you don't remember how to do that, you might want to watch the lesson on converting between number bases again. But we're done. We've put this in binary form. Now we want to change this to normalized binary form, which means we put this in binary scientific notation. So we're going to move the decimal way over here so that our number becomes negative 1.001. 0, 0, 0, 0, 1, 0, 0, 1, 1, 1. Now how many places did we move it? We moved it 6 places to the left, and so we're going to multiply that number by 2 6 times to return the decimal back to where it was, and we have this in normalized binary form. And we're done. Okay, we're going to build on that, so that's definitely something that you should do for practice now. I want you to pause the video, take a piece of scratch paper and your calculator, and convert 34.65 base 10 into binary and normalized binary form. Okay, here we go. We're going to start by turning this into binary. You might kind of recognize that you can get pretty good at converting these to binary without writing out that binary conversion table. The biggest power of 2 that fits into 34 is 32, so we're going to put a 1, and I'm just going to note here that that is the 32 place. And so we'll take 34 minus 32, and that leaves us with just 2, and that means that there are no 16s, no 8s, no 4s, a 2, and no 1s. 32 and 2 gives us our 34. Then we're going to have our binary point, and to get our binary places, we're going to take our decimal of 0.65 and start multiplying it by 2. Times 2, we get a 1. Subtract that off. Times 2, we get a 0. Times 2 again, there's another 1. Subtract. Times 2 is 0. Times 2 is 0. Times 2, we get a 1. Now you might say, well, how far do we go? We're going to answer that question in just a minute, but for right now we'll go 8 places. Subtract off that 1, times 2, we get another 1. Subtract off that 1, times 2, and we get a 0. That's good enough for now. Okay, by doing that, we've put this in binary form. Now to put that in normalized binary, we're going to put that in a binary scientific notation. So we're going to have to move the decimal 1, 2, 3, 4, 5 places to the left, and this becomes 1.00011010010001110 times 2. We went 5 places to the 5th, and that is normalized. Okay, well, let's do one more example with a real small value, like this one, negative 0.0341. Those are actually a little bit easier because there's no front number that we need to convert to binary. We just need to convert the decimal part of this number. So here we go. We know it's going to be negative. Let's convert that to binary. Negative 0.0341. We're going to multiply that by 2, and we get a 0 times 2. We get another 0 times 2. We get another 0 times 2. Another 0 times 2. There we got a 1. So we'll subtract that off and keep going. There's another 1. All right, and that's plenty of places for what we're doing. There, we've got this in binary form. Put it in normalized binary. This time we're going to move the decimal to the right. And so we're going to go 1, 2, 3, 4, 5 places to the right. This number in binary scientific becomes negative 1.0001011. And times 2 to the, now we moved it 5 places. But this was a really, really small number, and just like in scientific notation, those are negative values, and so that would be times 2 to the negative 5th, and there's our normalized binary. Okay, so now what we're going to do is we're going to take that number written in normalized binary form, and we're going to kind of package up all that information using 32 bits, that is to say using 32 ones and zeros. So that is what the IEEE standard for System 754 is. Let's start with the number negative 248.75 base 10. Well, the first thing we need to do is we need to recognize that this number is negative, and we'll put that into our format in just a minute. The next thing we need to do is convert this number into binary form. So we'll start with the 248. I trust that you could do that at this point by using a conversion table, but the number 248 becomes 11111,000. Then of course we would need to convert the 0.75 into binary. There's our binary point, and here we go. 0.75 times 2, that gives us a 1. Subtract off the 1 times 2, and that turns out to be a 1. And at that point we have 0, and so the rest of our digits will be 0. That repeats. So we're done converting to binary form. Now we're going to convert to normalized binary form, which means we're going to move our decimal 7 places to the left to get 1 point. It's going to end up right here. 1111 0 0 0 1 1, and then zeros for the rest of the way, times 2 to the, it took us 7 places to do that. This is a large number, so times 2 to the 7th. And now we're in normalized binary. The third thing we need to do is we need to work with our exponent here. Our exponent is 7, and that'll always be an integer. But to work in this system, we will always add 127 to that. And that means if that were a negative exponent, it will become positive. So that means that our exponent value here is 7 plus 127, or 134. Now 134 converted into binary is going to consist of 1 0 0 0 0 1 1 0. That's a 2, a 4, and a 128. And at that point we have all the information we need to write this number using 32-bit storage. Here we go. Our first digit is our sign bit. So since this is a negative number, we're going to start out with a 1. Our next 8 bits represent our exponent. Our exponent here is 1 0 0 0 0 1 1 0, and so we're going to put that in our next 8 slots. The next 23 slots are reserved for our normalized mantissa, or the number in front of the 2 when we're in normalized binary form. But when we're in normalized binary form, this number in front always will be a 1, every single time. And so since it's always a 1, we don't need to specify that. We can ignore that and take the rest of these digits and put them down here. So we have now, I've moved all the digits down here, but we have 23 digits available to us. We haven't used them all. So far we've used 1 digit here, 8 digits here, and so far we've used 10 digits here. That's only 19 digits used. We get 32, and so that means there needs to be 13 more digits until we're out to a full 32. And so there's our complete number in 32-bit form. Now, these can be blocked into groups of 8. And there's 4 groups of 8. Notice though, and be careful, because the exponent bits, because of the sign bit, run 1 into our mantissa section, and that's why we only get 23 digits for the mantissa. And that matches the representation on your screen, and we're done. Okay, let's do another example. This time as we work through the process, we'll fill in those 32 bits right on your screen there, so you can watch our progress in that way. Let's convert the number 4,827.211 that's currently in base 10 and store it using this 32-bit system. So first of all, let's write our number in binary. We'll begin by representing 4,827 in binary. I know that you could do that process using a conversion table. That's a little bit bigger number than we've worked with before, but I'm sure you can handle it. And there's our binary representation of 4,827. Now that is negative, but we'll work that into our format later. Next, let's convert the decimal. 0.211. We'll take 0.211 times 2, and we get a 0. Times 2 again, and we get another 0. Times 2 again, we get a 1, and we'll subtract that off. And I'm going to let you work out the rest of this process. We've done that several times. I'm confident you could get this. Now at this point you should ask, well, how do we know when to quit? Well, here's the key. Remember, we only get 23 of those 32 spaces to represent this number. So once we've got 23 total places, we can quit. But remember, we're always going to throw away our leading one, and so we can ignore that. Let's count how many places we're at. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. We're at 23 right there, and so we can stop because we have 23 total places. Anything beyond that won't fit in our number scheme anyway. Now let's put that in normalized binary form. We're going to start with 1 point, and how many places do we have to move that decimal? We have to move it 12 places. So this is going to be 1 point. And we've got this in normalized form. So what's our exponent going to be? In this case, our exponent is 12. We always add 127 to that, and so our exponent here turns out to be 139. The binary representation of 139 is 10001011. And at that point, we can put our number into those 32 bits. This was a negative number, so our first bit, the sign bit, will be a 1. Our next 8 bits are occupied by our 8 exponent places. And the next 23 places are all the points to the right of our binary point when it's in normalized form, because again, we know that that's a 1 and we disregard that. And there's our number stored using the 32-bit number system. Okay, here's one for you to do for practice. Convert 0.001372 into the 32-bit storage system. Unpause when you're ready to see if you have all those ones and zeros in the right place. Okay, here we go. So we need to convert 0.001372 into binary. There is no whole number in front, so we don't need to convert that. All we need to do is convert the decimal part of our number into binary, and you know the process there. We're going to start multiplying by 2 repeatedly. I'll let you go through that process. Here's what you should get. Okay, well, it took quite a while before we even got to a 1 there because that number is so small. And I actually had to wrap that onto 2 lines, which is a little sloppy, but if I write any smaller, you won't be able to see that on your screen. So let's switch that to normalized form now. We're going to move our decimal point all the way over to right here where that first 1 is. So we made a 10-place move there. Our number in front will be 1 point. Now, we need 23 places here. I don't even know how many I wrote, but I know that after the 1, I need 23 places for our number. So here we go. There's 6 up to there. Okay, I've written this in normalized form. I've gone 23 binary places. I actually had more than what I needed up there. And since we moved that 10 places, and this was a very small number, that's 2 to the negative 10th. So what's our exponent going to be? Your exponent should be Negative 10 plus 127, that becomes 117. And 117 in binary is 01110101. And now we're ready to put that into our 32-bit form. This was a positive number, and so our first digit will be a 0. Our next 8 digits are our exponent of 117, and that leaves 23 more digits for our binary places from normalized form. As always, we're going to ignore that one and keep the rest. Makes it a little bit easier if we break those into groups of 8, and that's what you should have in 32-bit form. Okay, let's wrap this up by going in the opposite direction. Let's take a number stored using the 32-bit format and figure out what number is being represented. So on your screen here, I've got a 32-bit number broken into 4 8-bit chunks by color. Let's decode that one. We'll do this one together, and I'll give you one for practice. So the first thing we want to do is we want to break it up according to the 3 parts of the number. The first digit we're going to break off, that's our sign bit. The next 8 digits give us our exponent, and the last 23 tell us what our mantissa is. So here we go. Our sign bit is 0, that means this number is positive. Our exponent is 10001001, and if we convert that into binary, we have a 1, no 2s, no 4s, and 8. No 16, 32, or 64s, and a 128, which means our exponent is 137. Now remember, our exponent value is 137. Our actual exponent, our number, won't be 137 because that had 127 added to it. We need to subtract 127 as we always do, and that means our exponent value here is 10, and that's the number we'll need in just a minute. Our next step is to figure out what the number would be written in normalized binary notation. So there's all of our significant digits, or our mantissa. Now remember, we always ignored the 1 in front of the binary point. So if we take this number and write it, we're going to have 1 point. Okay, that's always understood, followed by all these binary places. Now in this case, we have a few 1s and 0s, and then a bunch of trailing 0s. We don't need to write those. So we have 1.011011101, and then a bunch of 0s times 2 to the what? Well, our exponent was 10, so that's times 2 to the 10th power. We've got it back into normalized binary form. Now let's switch that into binary form. This is a pretty large number because of our positive exponent here, and in fact this tells us that this is our binary number if we move it 10 places to the right. If we move it 10 places to the right, our decimal will move all the way down to here, and so there's our binary number. We ended up with no 1s to the right of the binary point, and so apparently this is going to be an integer. And what integer is it going to be? Let's let our calculator help us out here. We have no 1s, a 2, no 4s, an 8, a 16, a 32, no 64s, a 128, a 256, no 512s, and a 1024. And so we get 1466, base 10. We knew that that number was positive, which means we don't need to change it to a negative sign, and there's our result. Okay, here's one for you to do for practice. Take a minute and convert that number into a plain old decimal number, given that it is stored using our 32-bit storage system. Okay, here we go again. By some means, break that number into its 3 parts. The sign bit here is 1. That tells us that this number is negative. Our next 8 bits give us the information we need to find our exponent. 1 plus 4 plus 8 plus 16 plus 32 plus 64 gives us 125. As always, we need to subtract 127, and that leaves us with an exponent of -2. We'll use that in just a minute. Let's write this number in normalized form. We know we're going to start with 1 point something, and 1 point what? Well, it's going to be 1 point and all of these digits after the binary point. We can quit after the last one. It's zeros, everything after that. And so it'll be 1.10001100101 times 2 to the -2nd power, which means that we're dealing with a small number here. Now that we can rewrite that in binary, we'll move our decimal places 2 spots, and since it's a negative exponent, that means this is a small number. We need to go to the left. So in binary, this is 0.011000011000101. Okay, so now we need to expand this to figure out what the value of that binary number is. It's clearly a pretty small number. So we haven't done this since we first started working with binary numbers, but let's do our expansion. Remember, this spot right here is 2 to the zeros place. This spot right here is 2 to the -1's place. We have neither of either of those. So this number is going to have 1, 2 to the -2, plus 1 times 2 to the -3, 2 to the -4, 2 to the -5, 2 to the -6, 1 times 2 to the -7, 1 times 2 to the -8, no 2 to the -9, 2 to the -10, 1 times 2 to the -11, 12, and 1 times 2 to the -13. And that becomes calculator work. You can enter that into your calculator. Remember that if you don't want to type all this into your calculator, we can just say that that's 1 over 2 squared. This is 1 over 2 to the 3rd, 1 over 2 to the 7th, and so on. That might make it a little bit easier to enter. And after you type all that in, you should get 0.387329. That's 6 significant digits. That's enough. We've got our value. Hopefully you got that. If not, go back and watch that one more time so you've got the process. But that wraps up what we need to do with that storage system. Okay, so really there's two big pieces of information to take away from that lesson. First of all, what is normalized binary form? It's a way of representing that number in sort of a binary scientific notation. We have a coefficient that always starts with a 1 and some power of 2 to represent both large and small values. Then we can take that number and all the information it contains, including its sign, whether it's positive or negative, the value of the exponent on that 2, add 127 of course, and then all the significant digits after the 1 in our number, and package those up using 32 bits, and that gives us our storage scheme. All right, well, a lot of ones and zeros there, but keep at it and let me know if you need help. I'm happy to meet with you on Zoom and work through a few of these if you're having any trouble. Good luck.